This is part 2 of reaction mechanisms, and on the last video, we were in the middle of determining if this was an acceptable mechanism. So we had already checked out that the rate determining steps rate law matched the experimental rate law, because if you write it from its molecularity, since it's bimolecular, we would have gotten rate is equal to K times concentration of NO2 to the first times concentration of F2 to the first. And then the video cut me off, so I'm going to pick up with the addition of the two elementary steps. All right, so we're going to cancel the intermediates. The intermediate here is fluorine. Okay, fluorine is the intermediate. That's the only thing that cancels. Since the NO2s are both on the reactant side, we're going to bring them down and add them together. So 2 NO2s plus F2 yields, these are the same, and there's 2 on the same side, so 2 NO2Fs, and that finishes it off. Okay, so now you want to check and see if they add together to give you the overall balanced equation. So we're going to compare, and when we compare, we have 2 NO2s, 1 fluorine yields 2 NO2Fs. So that part checks as well. Both of those check out. So you would say that this is a probable mechanism. So yes, it is acceptable. Okay. Now, if both criteria did not match, then you would say no, it's not an acceptable mechanism. So if only one passes a test, it would not be acceptable. Moving on to collision model. Collision model is just a model we use for kinetics, and the key idea here is that molecules must collide in order to react. However, only a small fraction of collisions produce a reaction. So let's talk about why that might be. The collisions must have enough energy, we call it sufficient energy, to produce the reaction. So what that means is they must collide with enough energy to meet or exceed the activation energy. Secondly, the colliding particles must be correctly oriented. So not only do they need sufficient energy, they must be oriented correctly so that when they collide, they can produce a reaction. So when they collide, they have to collide with enough energy to break the bonds. Now, there are some factors that affect your reaction rate, and y'all are familiar with many of these. Just think about things that you do, like if you were going to make some Kool-Aid or some tea and you wanted to sweeten it. We know that your sugar is going to dissolve faster if the water is warm. So just like with dissolving, when you're talking about chemical reactions, if you increase the temperature, that will always increase the rate of the reaction. Why? Because the particles collide more frequently, and if you can get the particles to collide more frequently and more energetically, then there's a higher chance that it will produce products. So the particles collide more frequently when you increase the temperature. They also collide more energetically. The second thing you can do to affect the rate of your reaction is you can increase the surface area of the reactants. This increases the rate of the reaction. The more surface area you have, the more particles can come into contact with one another, and therefore they're more likely to collide with the proper orientation and the proper energy. The third thing you can do is you can increase the concentration. That usually increases the rate of the reaction because the more particles you have present, the more likely they're going to collide, and as they collide, they're going to collide with more energy. A fourth thing you can do is you could introduce a catalyst to the chemical reaction. That would lower your activation energy and provide an alternative pathway for the reaction to produce products. So you can increase the temperature, you can increase the surface area, You can increase the concentration, or you can introduce a catalyst to the reaction. So let's look at this energy diagram. Here, this first line represents the energy of your reactants. The energy diagrams always have this hill you got to climb. We call this the activation energy. I think of it like a mountain you got to climb. The reactants must collide with enough energy to meet this activation energy. So this is to the top of this hill, this is your activation energy. Now what exists up here at the top, we call this the activated complex. Once the reactants have met their activation energy and collided with enough the proper orientation, then the products can form. So you'll notice it levels off here at the end, and this represents the energy of your products. Now the enthalpy value, we've talked about enthalpy a little bit with bond energy, that is equal to the difference in energy from where your reactant started to where your products leveled off. So we call this the enthalpy. And this is a positive enthalpy, meaning it's endothermic. Notice the energy of the products is higher than the energy of the reactants. Here we have an exothermic energy diagram. Energy of the reactants. Here's your activation energy. Again, what exists up here is called your activated complex, which is like in between the reactants and the products. And then the energy lowers, and notice the energy of your products level off again. So here you have this difference in energy. This is your enthalpy here. And this is an exothermic reaction. This has a negative enthalpy. I think I misspoke on the last slide, y'all, so let me go back to that. This is a positive energy exchange. This is actually endothermic. I think I said it was exothermic, and if I did, I apologize. Y'all were probably thinking, sorry. This is endothermic because the energy of the products is greater than the energy of the reactants. Okay? Here is our exothermic reaction. All right. And for some reason, I had written exo on this one before. Okay? Catalysis. Let's talk about that. There's, y'all are all familiar with enzymes. Enzymes are large molecules. Usually they're proteins, and enzymes catalyze our biological reactions. So the catalyst in our biochemical reactions are known as enzymes. You can have a homogeneous catalyst, or you can have a heterogeneous catalyst. Now, homogeneous catalysts are catalysts that are present in the same phase as the reacting molecules. So, like if your reacting molecules were all aqueous, then you added an aqueous catalyst, that would be a homogeneous catalyst. Or if they were all gases, that would be homogeneous. A heterogeneous catalyst is present in a different phase than the reacting molecules. So, for example, if your reacting molecules were gases, but then you added a solid substance or an aqueous substance as your catalyst, that would be considered heterogeneous catalyst. Remember, a catalyst is a substance that speeds up the reaction without itself being consumed. Now, the way that the catalyst functions is it lowers your activation energy. So this dashed line here, if you look at your energy diagram, represents the pathway that the catalyst provides. It provides an alternative pathway with a lower activation energy. Notice here the activation energy is lower with the pathway of the catalyst. So a catalyst is kind of like a hill, a mountain you're trying to climb. It tunnels through that mountain and lowers the activation energy. And so you're able to get to the final state quicker. Notice these again would be your reactants.